Lenz's law 1. Lenz's law says that the direction of any induced current will be so as to resist the change in magnetic flux. Incidentally, this direction here, the direction of any induced current, also, right, the direction of the induced electric field and the EMF, which is represented by this capital E that has panache. So all those, that's what Lenz's law deals with, the direction of the induced current, the induced EMF, the induced electric field, and it has to do with the negative sign in Lenz's law. Lenz's law is an expression of the law of conservation of energy. So basically, Lenz's law, you might remember Faraday's law, one formulation of it looked like this. Lenz's law has to do with that negative sign right there. So let's investigate that. This will be the last right-hand rule that we learn in these videos, but it's a really useful one. We're going to go through the steps here, and I'm going to go through them quickly. They might not make a lot of sense, but then we're going to do some examples, and hopefully things will become clear after that. So first, we have to have a conducting loop. Inside of this loop, the magnetic flux must be changing. That is, it must be increasing or decreasing, and we have to know which of those it's doing. So that's the first thing. Secondly, in accord with Lenz's law, we then figure out, by thinking, which way the induced magnetic field inside the loop will want to point. We're personifying here, but the induced magnetic field is going to want to point in a particular direction. And what direction is that, Mr. B? The induced magnetic field will want to point in such a way as to try to offset or minimize whatever change there was in the flux that we identified in step 1. So we'll demonstrate this with examples here presently. Point number 3, we point our right thumb in the direction the induced magnetic field wants to point, as we deduced in step 2, and then our right fingers will curl in the direction of the current or the electric field, right? All of these things will point in the same direction, or the EMF. All of those, they all point in the same direction that we figured out. That's the direction our right fingers are going to curl. Now, probably that didn't make a lot of sense, but hopefully it will after we do a few examples. All right, let's look at this picture in the left side of the screen here. We have a loop, a conducting loop, and we have a magnetic field that's pointed towards us. We know that because of the dots. And we're told that the magnetic field is increasing. So the magnetic field is coming towards us, and it's increasing. And what we want to do is we want to use our right thumb, and we want to use that right thumb to resist any change. And if the magnetic field is coming towards us and getting bigger, we fight with our right thumb. We say, you know what? I don't like it increasing, coming towards me. So I'm going to fight it with my right thumb, and that means I'm going to fight it by pointing down. And which way do my right fingers curl? They curl clockwise. So the induced stuff, the electric field, the induced EMF, the induced current, if it's a conducting loop, in this case, are going to point clockwise. Let's try the next example. Here, the magnetic field is directed into the page, but it's getting weaker. And basically, nature says, okay, shall I put it up here? I don't like change. That's what nature is saying. I don't like change. When? And if the magnetic field is directed into the page, but it's getting, we say, you know what? I don't like it getting weaker. I like it the way it was before. So we're going to use our right thumb and we're going to help. We're going to help by pointing into the page. Which way do our fingers curl? Also clockwise. So induced current is going to go clockwise in that case as well. How about the next one? Here, the current is coming towards us, but it's continually getting weaker. What does nature say? I don't like change. I don't want it to get weaker. I want it the way it was before. So I'm going to use my thumb and I'm going to try and help. Which way do our fingers curl? Counterclockwise. How about on the right? The magnetic field is going into the page. It's getting stronger, stronger, stronger. Nature says, I don't like change, so I'm going to fight the change. And if it's increasing into the page, then in which way is the induced stuff, the electric field, the EMF, the current? Counterclockwise. Here. Here we have a constant, the current. So we have field lines that are going into the page here, current. And as we get further away, the field gets weaker, doesn't it? As we move the loop away, there's going to be less flux. What does nature say? I don't like change. So if there's less flux, we're going to try and help by using our right thumb, and we're going to end induced current and EMF. And how about this one? We're moving the loop towards. Now here, on this side, isn't it true? Field lines are pointing into the page. And as we move the loop closer, there's going to be more into the page flux. We're going to fight that with our thumb. We don't like more into the page flux. We like it was before, counterclockwise. We've got to the right, so that means by the thumb can twist and right hand rule, we have magnetic. As we move the loop this way, there's more into the page flux. Nature doesn't like change. I'm going to fight that. There's more counterclockwise. Last one on this page. We're moving the loop away. The magnetic field is stronger here. It's weaker out here. As we move it away, the flux is into the page and it's getting weaker. And we don't like that. We're going to try and help it out. We don't like it to change. So you're going to use your thumb and help it out and try and boost. A couple more. Here we're holding the loop steady and the current is increasing. So here we're going to have the current side, and if the current is increasing, that means that the flux into the page is increasing. We're going to fight that with our thumb. We're going to go counterclockwise. So for this example, we've got to the right, but the current is decreasing. It's getting less and less. So that means that the magnetic field out of the page, by the thumb can twist and right hand rule, right? So these field lines are coming out of. There are a whole bunch of them here. The further away we get, the gets. And if the current is decreasing, that means that this out flux through this loop is going to help it out.